Today we're going to be talking about Chapter 3.1, which is over scatter plots and correlation. Correlation is generally defined by the variable r. So the two variables that generally explain a scatter plot are the explanatory variable, which is the x, and the response variable, which is y. In layman's term, explanatory variable would basically be the independent variable, and response variable would be the dependent variable. An example of an explanatory variable could be time studied on a test. The response variable for this explanatory variable would be the grade you make. So if you put in 1 hour to study on the test, you might make a C. If you put in 5 hours to study for the test, you might make an A. So 1 hour might correlate to 75, 3 hours might correlate to 95. The scatter plot basically shows the relationship between two quantitative variables. This basically implies that a scatter plot cannot show the relationship between two qualitative variables or categorical variables. Two quantitative variables, as we defined earlier, could be time studied and the grade made for a test. These are obviously quantitative because a number value can be assigned to them. Two variables that a scatter plot may not be able to explain would be color and mood. It'd be hard to explain the relationship between red and rage on a scatter plot and blue and calm on a scatter plot because they're not quantitative variables. Therefore, you need quantitative variables in order to accurately depict the relationship between the two. For any FRQ question or any stats question, you should, when looking at a scatter plot question, there are three things you should go through, or three metrics of evaluation. The first would be the strength of the data, which can be defined, as I said before, by R, otherwise the correlation. R is usually between -1 and 1. The closer it is to the poles, i.e. -1 and 1, the stronger the correlation. So if you look at a scatter plot and the data is random, you don't really see a relationship between the explanatory and the response variable, the R value would probably be closer to 0 rather than say 1 or -1. Also, you should also be able to interpret the direction, whether the data is positive or negative. A positive correlation would imply that as the explanatory variable increases, the response variable also increases. A strong positive correlation would posit an R value of 1. A negative correlation would be when the explanatory variable increases, the response variable actually decreases. So this could be the number of ice creams you eat, and which would be the explanatory variable, and the time you run a mile, which would obviously decrease as the number of ice creams you eat before you run the mile increases. That would be a strong negative correlation. The last metric of evaluation would be whether the data is linear or curved. A data which a LSRL, or least square regression line, could accurately define would be linear, as the points actually line up together in a linear format. That would be a linear relation. A curved relation would be one in which, as the explanatory variable increases, the response variable doesn't increase at the same rate the explanatory variable does. It increases at an increasing rate. That would be a curved relationship between the explanatory and response variable. So these three metrics of evaluation should always be considered when you're looking at any sort of stats, FRQ question, or multiple choice question regarding scatter plots and R correlation. So for the visual learners out there, I've created 4 different scatter plots, each with varying degrees of strength and direction, positive or negative. The first scatter plot right here would have an R value close to 1, and the direction would obviously be linear and positive. The second scatter plot would have an R value closer to -1, and the correlation would be negative, and the data would be linear. So just for the sake of examples, in the first one we have on the x-axis time studied for a test, and on the y-axis we have the grade made on the test. Logically, we think that those have a strong correlation, thus positing a R value close or at 1. The third and fourth scatter plot both show positive and negative directions respectively. However, the strength of the correlation is pretty low as the R value is close to 0. Though you can draw an LSRL, it's a bit harder to predict exactly where the line would fall because of the low correlation value. So this is basically going to be a review slide over scatter plots and correlation in case you weren't listening. As I said earlier, the R value is always going to be between -1 and 1 inclusive. The closer it is to -1 or the closer it is to 1 implies a stronger correlation between the explanatory and response variable. Obviously, as R gets closer and closer to 0, the correlation between the points becomes more and more non-existent and harder to see upon sight. Something else to note is that R is not dependent on where the x and y variable are. So if you switched Mile time and ice creams eaten, or Mile times ice cream eaten from the y to the x, the r value would not change, meaning that the r value is actually independent from, it basically doesn't make a distinction between the explanatory and response variable. It's also important to note that the scatter plot would actually not change when units of measure change, right? So if you change perhaps weight from kilograms to pounds, the scatter plot would not change because the correlation is dependent on the standardized value rather than the value that is given when the units are assigned. Also, because of that, you get to the fourth point right here, that correlation has no units. The R value, it's not R feet, R inches, it's just an R value. There's no units attached to it. It basically describes the strength of the correlation. And this is true even when, the equation changes. So this basically sums up chapter 3.1 on scatter plots and correlation. I hope you understood everything, and good luck reviewing.